All right, so we are going to be doing a bit of a lesson on circuits. And realizes this is a little bit more of the conceptual end of circuits because I do have another video that goes over like the how to do circuits in terms of finding the voltages and the currents and whatnot. But I want to cover a bit more of the conceptual end of things here a little bit more. So what do we have here? What are we looking at? So this is the voltage that you get across a battery. This is the EMF. EMF is electromotive force. It basically is voltage. It's measured in volts. It is effectively voltage, sort of. It's the ideal voltage of a battery. So it's the ideal voltage of the internal voltage. It is the voltage that the battery would have if it didn't have any internal resistance. Now remember that V equals IR. So this part here is the reduction in voltage, or the voltage drop, because of the internal resistance of the battery. So to make more sense of that, let's take a look at a picture of a battery and make a little bit more sense of it. So here we have the two terminals of the battery. The A and B terminals are the positive and negative terminals of the battery, the cathode and anode respectively. If you were to take a voltmeter and measure the voltage across these two terminals, then you would have a voltage, what's known as a terminal voltage, of VAB, meaning the voltage across terminals A and B. The E symbol here, I believe that's a capital epsilon, correct me if I'm wrong, but this here is the ideal battery that you would have internally. And then in series you have a resistor. So essentially any real world battery is composed of a virtual battery on the inside of it, along with some sort of virtual in-series resistor. Because the chemical reaction that happens inside of a battery can only happen so quickly, and there's going to be some amount of actual resistance internally inside of that battery that causes the flow of current to be restricted in some way. Now, the amount of restriction that occurs is partly dependent on the current. So essentially, when we look at this equation again, if you notice, since V equals IR, if I have a lot of current in that battery, then the voltage drop that's occurring here is going to be more, where the EMF does not change. So what does that mean? Well, I've talked before about how if you have like a car and you turn the ignition to the on position but don't actually start the car, and you turn your lights on. So your lights are going to come on at their full brightness, and they're going to stay like that for the majority of the life of the battery. However, when you go to actually start the car, there's so much draw of power for the starter of the car. There's so much draw of power from the battery that it's going to dim the light bulbs. And this is in large part why? Because as the current that flows through the battery is so large, the current is going to cause that resistor to draw a lot of a lot of voltage. So there's going to be a large voltage drop. So when we look at this equation, if the current is large, that resistor is going to cause a large voltage drop. So let's say that we play with some fake numbers. Let's say that we have a car battery. And let's say that the internal battery has a voltage of, let's say, 13 volts. However, there's an internal resistance that typically would make the terminal voltage about 12 volts. But when you go to actually start the car, there's so much current being drawn through the battery that it causes the voltage drop not to be 1 volt, right? This is 13. It causes 1 volt to drop. That gives you 12 volts across the terminals. But what if so much current is drawn through that battery that this internal resistance causes the voltage drop here to be, like 5 volts, right? So in that case, then you would drop down to, what did I say? Start off at 13, so it would be down at 8 volts, right? So that would definitely cause your lights to dim as you're starting the car. So that would be an example. Okay, so we treat all batteries as if there is some sort of virtual ideal battery with a resistor in series with it. Speaking of series, when we look at a series circuit, that means that you're going to have one resistor after another after another. That means that any current that goes through the first resistor must also go through the second resistor and the third, and so on. It is a series of events. Hence, it's a series circuit. So a series of events means that one thing happens after another, and so that's what a series circuit is. Here we have the symbol for a battery where the large little hash mark here is the positive end of the battery, and then here is the negative end of the battery. And so the current is going to flow in this direction. It goes through the first resistor, and then through the next resistor, and so on. And so remember that each resistor gets the full amount of the current, and the battery gets the same amount of current as well. The current is the same for all resistors. However, the voltage is split. Let's say, for example, that this is a 12-volt battery. So the voltage here at this part of this line would be 0. The voltage here would be 12. That's what the battery does. It pumps the voltage from 0 to 12 volts. So we have a voltage of 12, and then there's a voltage drop across the first resistor. So let's say that all resistors are the same resistance. It would cause an equal voltage drop across all three resistors. So if we have 12 here, each one would drop 4, right? So it would go from 12 to 8, and then to 4, and then 0. And so the voltage is split between the three resistors. If they are not all the same resistance, then the voltage split would not be equal between the three. And so the one that has a larger amount of resistance would have a larger voltage drop. Remember, V equals IR. So if this one has the same current as the rest, so the value of I is the same, but the value of R is larger, V equals IR, that means that larger R equals larger V. So that means that this would have a larger voltage drop across it. I'm going to make an analogy to make this more intuitive, but I want to talk about parallel circuits first before we get there. So this is a little bit of the logic as to why it is that we add up the resistances to find the equivalent resistance, whereas since the voltage is split between all three, this gives you the voltage total, V equals IR, and the current is the same between all three, which means that you add up the resistances to find the total resistance, because the total voltage is equal to IR total. So that means to find the equivalent resistance for all three resistors put together, you just add them up. Meaning that if I were to look at these three resistors, I could take them out and replace them with one resistor in their place with some equivalent resistance. It's as if you take them all out and put that one resistor in its place. Now for a parallel circuit, in this case the current is being split because the current can go through pathway 1, pathway 2, or pathway 3. The voltage is the same for all three. So all of this area here is 0 volts. It goes across the battery and it gets pumped up to, let's say, that 12 volts. All of this area would be all 12 volts, and through all three resistors there's the same voltage drop. But the current is split. Some of the current goes this way, some goes this way, and some goes this way. This is the symbol for a resistor, quite obviously. A light bulb performs pretty much the same thing as a resistor functionally, other than the fact that it reproduces light, but otherwise in a circuit it's pretty much the same thing as a resistor. It often will have a slightly different symbol, but it's pretty straightforward. So let's take a look at the equivalent resistance for a parallel circuit. In this case, since the current is being split, the current of all three of them added up gives you the current total, and current total is equal to voltage over the equivalent resistance, right? So it's the total voltage divided by the total resistance. So since the voltage is the same, they have the same voltage drop, so that means to find the equivalent resistance, 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, which is represented here. So this is how you find the equivalent resistance. Be careful not to make mistakes with this. First off, obviously find the common denominator and add up these resistances, where you're adding up all the reciprocals. Then when you're done, find the reciprocal of that to actually find the equivalent resistance. So what I mean is, let's say that we have, let's come up with an example here. So let's take a look at an example here where we have, let's say in that same sort of circuit, that parallel circuit where we have the battery, and then it splits off into 3 segments like this. Something like that. And there's a million different ways to draw it. So as long as this is all connected, right, as long as it's all connected, then this is all a voltage of 0, and then on this side, this would all be a voltage of positive 12. And I think I'm off of my page, aren't I? Because I'm brilliant. Ha! Let me try and do that again. Oh, look, there it is. So, so over here we have a voltage of 0, over here we have a voltage of 12, and then they split up. So we have resistors 1, right? I'm just going to say 1, 2, and 3. Okay, so let's make up an example of some kind. So what if we have where R1 is equal to, let's just say it's 2, a resistance of 2, and let's just say that both of these here, so R2 is equal to 1 ohm each. By the way, here's the symbol for resistance, right? So this one here is also 1 ohm. So what do we do with that? Okay, let me see if I can actually take this and move it a little bit out of the way. Make sure that I'm still on my screen though this time, because that would be brilliant. Okay. Better. Aha. Okay, so that means that what I'm going to do is I'm going to rewrite this part. So 1 over the equivalent resistance is equal to 1 over 2 plus 1 over 1 plus 1 over 1. Well, the common denominator is 2, so I'm going to just kind of rewrite that real quickly. So 1 over the equivalent resistance equals 1 over 2 plus 2 over 2 plus 2 over 2. Right now I have a common denominator, add them all up, so I would find that this is 5 over 2. And so 5 over 2, is that my resistance? No! Because 5 over 2 is equal to 1 over the equivalent resistance. So 5 over 2 is equal to 1 divided by the thing that I'm looking for. So that means that the equivalent resistance is equal to the reciprocal of this. So that means 2/5 is equal to my my resistance. So my final answer should be 0.4 ohms as my resistance. Okay, so that's an example of how you solve for the equivalent resistance. All right, let's see here. I think that I'm going to do some analogy time. Woo, story time. You ready? This is going to be good times. Okay, now I like to do 2 different analogies for series and parallel circuits. So I think with the first analogy, it's going to be something that is a little bit more in the way of something that's reasonable, and then the other one's going to be more ridiculous. So that's okay. So let's see the somewhat reasonable sort of analogy. One analogy that I like to make is a koi pond, right? So some sort of like backyard kind of pond where there's water and a pump and maybe a decorative waterfall. You know, your dad decides to go a little bit crazy this summer and says, you know what, I'm going to make a koi pond. Go dig a hole. And then you dig a hole for dad, and then he like gets out a water pump and he makes some sort of like water feature. And you're like, this is your more reasonable example? Yes, for me it is, because I dug a lot of holes for Dad as growing up. So here's my analogy. This area here, all is 0 volts. So all of this area here would represent ground level, a height of 0 feet. All of this area here. Then this would be the pond, okay? This here represents a pump. It would be like a water pump. Now, in actuality, it's a battery and it is a voltage pump. But in my analogy, we're talking about a water pump. And so what it's going to do is it's going to pump the water from a height of 0 feet up to a height of 12 feet, or 12 volts. So all of this area here would be sort of like maybe some sort of like upper small retaining water level. And then these would be a series of waterfalls. So the water is at 12 feet. If all of these waterfalls are the same, then it drops over the first waterfall. Now it's at 8 feet. Then it drops over the second waterfall. Now it's at 4 feet. And then it drops over the third waterfall, and it's back down to the ground level at the koi pond. Okay? So this is like a koi pond with some waterfalls, where we have a pump, and then we have these voltage drops. If this one has more resistance, then there's going to be a larger drop here. My analogy does fall apart a little bit in that case, but if the resistance and restriction is larger, there would be a larger drop here than for the rest. I think that my analogy really comes together nicely in parallel, okay? So here, all of this area over here is all ground level. So anything that is touching, right? Remember that wires in a circuit diagram all have a resistance of 0 unless stated otherwise. So that means that all of this stuff that's touching, it's all ground level. Okay, there's no devices. Up until there's any devices, it's all ground level. It's all 0 feet or 0 volts. Here's the pump, pumps it up to 12 volts or 12 feet. All of this would be the same height of 12 feet. Then it hits 3 different waterfalls. These 3 waterfalls are all in parallel. They're all right next to each other, and they all are the same height. They all fall together. Let's say that one waterfall has a larger amount of resistance. It has a larger restriction, meaning maybe there's something there to restrict the water, like some sort of screen or blockage or whatever it might be. Even though it might have the same height as the other waterfalls, you should recognize that it's going to have less flow going through it, so it will have less power as well. That should make sense. That's going to mean that the water is going to go through the other 2 resistors more, because this one has more restriction or resistance. So they all have the same voltage drop. They don't necessarily all have the same resistance. And so therefore they wouldn't necessarily all have the same current. Okay? So I hope that those analogies help a little. Now, time for analogy number 2. This one, maybe not as intuitive, but I think maybe people kind of remember it a little bit more because it's kind of silly. So let's go back to this first one. Here's my analogy. Walmart! You see, here I am loading up my grocery cart. That's the battery, because I'm putting stuff in the grocery cart, and I want to get out the front door. My analogy really just kind of refers more to the idea of the equivalent resistance. Before I can get out to the front door, which is over here somewhere, I have to go through these resistors. So what are the resistors in Walmart? So I go to the cashier. That's my first resistor. Now, if the cashier is a lovely elderly woman who maybe is moving a little bit slow, has the little hand thing on there because she's got carpal tunnel or whatever it might be, bless her heart, she's just moving a bit slow. So she's going to have a lot of resistance. And I finally get through that line. And then I go to get out the door, and then what happens? They check your receipt. Are you stealing anything? Let me check your receipt. Okay, yeah, let me stand here while you check that receipt and whatever. And then you think you're finally free. And then there's the girls selling the Girl Scout cookies, because it's that time of year, right? And so it's yet another bit of resistance preventing you from leaving the door. You go through one, and then you have to go through another, and then you have to go through another. By adding more resistors, you now have more resistance allowing you to get to your car and get the heck out of there, right? So by adding resistors when in series, you're adding and increasing the equivalent resistance. However, what about in parallel? Does that make sense for a grocery store? Yeah, actually it does. When I am at the grocery store, I want them to add more resistors because that's going to make it easier for me to get through when in parallel. What do I mean? Well, these would be cashiers, right? Here I am, and I'm trying to get to point B, which is the door. Okay? So each one of these would be a different cashier. Do you recognize that having 3 cashiers as opposed to 2, right? Having 3 cashiers would make the lines go faster. More people can get through more quickly. These are resistors, right? They are a resistor. They will not let you leave the store until you pay for your stuff. So if I add in a 4th resistor, is that going to make it easier or harder for me to leave the store? Easier. Because I have yet another pathway through which I can go, and everybody can kind of flow their own way. So this is like the lines at the grocery store. It's like Mark's, and I'm not even joking. I think about it every single time I'm in Mark's, because every single time I'm in Mark's, there's not enough lines, and that's why I don't go to that stupid store, right? Because when I go in there, there's like one line for like 20 people, and then you hope and pray that they're going to actually open up the line. And so, Reese, you know exactly what I'm talking about. Feel offended all you want. You know it's true. All right, so those are my analogies, and hopefully that kind of helps that stick in your brain a little bit. Kirchhoff's rules. Well, that looks complicated, doesn't it? And guess what? It is. But it's actually kind of fun when you learn how to do it. I have a separate video that goes off of Kirchhoff's rules, though, so I'm going to honestly save that for another time. Do notice that there is more than one battery in this case, and those batteries kind of oppose each other a bit. We'll get into that in a different video, so I'll just kind of skip right along. There is something else I would like to get to, so there's the loop rule, da-da-da-da-da. Aha, here we go. So, batteries in series and together in circuits. Now, this isn't really Kirchhoff's rules. I can explain this without that. These 2 batteries are in series, and they're both trying to push the current in the same direction. Their voltages would add, okay? The voltages of the batteries would add, and so we would have a 3-volt system in this case. Do the batteries have to have the same voltage? No, they can have separate voltages. So let's say that one is 1.5 and the other one was 3. I would have a total of 4.5 volts, and it's okay to do that. In this case, I have 2 batteries that are of different voltages. Is this okay to do? Yes, but what's happening here? In this case, I'm recharging a battery. So I have a battery here that is at least supposed to be a 12-volt battery. Maybe it's actually more like running at 10 volts because it's been discharged and to the point to where it's actually not running the correct voltage. And this voltage is much larger. Notice how they're opposing each other in this case. So this battery is going to overtake the other, right? It's going to force current to flow through this battery in the wrong direction. In doing so, it's going to reverse the chemical reaction of the battery. Now, don't go trying to do this with alkaline batteries. That's just not good, right? To be honest, it can be done for like a few seconds, and you might get a little tiny bit of charge out of a battery, but it's not worth it because it can explode, and that's just bad. You don't want extremely basic or extremely acidic materials on you, so yeah, don't go charging batteries that are not meant to be recharged. But this is the general basic idea of recharging a battery. You're forcing the electrons through in the opposite direction. Now what about in parallel? These are batteries in parallel. Notice how these are also the same voltage. In this case, you are not increasing the voltage. Okay, you're not increasing the voltage of the system. Instead, the voltage of the system is 12 volts, which is the same as the voltage of each individual battery. But in this case, you are allowing the system to run for a longer period of time. You are increasing the available amperage for whatever this device is, this resistor. Should these two batteries be the same voltage? Just like in series, where these can be separate voltages, what about in parallel? Well, yeah, these ones have to be the same. It is a bad thing when they are different. So basically, you're going to have, let's say that this one had a higher voltage. Power would go through this battery. It would push through, and then since this one has a lower voltage, this battery would wind up pushing not electrons, but current through. It would push current through in that same direction way more than what this battery wants to do. And it would essentially cause major problems. This is the sort of reason why when you jumpstart a car, right, you have one car that's running fine and another car that has a dead battery. That dead battery has a voltage that is lower because it's so low of a voltage that it won't even start the car. So when you jumpstart a car, you put positive to positive, negative to negative, right? You're putting them in parallel. So I said that bad things happen. Yeah, so you're actually running the risk of blowing up a battery. You know what you do to try and prevent that? Is the car that you are jump-starting, rather than connecting that negative terminal of the black cable, instead of connecting the black cable to the negative terminal of the battery, on the car that's being jump-started, you want to connect that black cable to the body of the car. You want to ground it to the car and make the current flow through that car, and it will minimize the surge of power into the battery, and it will help use your car as sort of a reservoir that can kind of help limit the surge that goes into the battery and prevent it from blowing up. You are running a risk that you're going to blow some fuses in your car that way, but it's a heck of a lot better to blow fuses than it is to blow up a battery acid all over you. So that is why you should, when you jumpstart a car, always put that negative black terminal or the black cable onto the body of the car, not onto the negative end of the terminal of the battery. That's the car that's being jumped. You should do that. Capacitors! Guess what? We're not really going to talk about capacitors. So I'm going to kind of skip that because we get more into that in AP Physics 2. And capacitors, yep, more about capacitors. Electrical hazards. I've talked about this. We'll just kind of recap it super quickly. In this case, what does a ground wire do? It's not necessary to actually operate a device, but rather the ground wire is connected to the body of the device. So that way, rather than the electricity flowing into you and then through your feet and into the ground, instead it flows through the path of least resistance through the ground wire, and that way it does not go into you because your body has much more resistance than the copper wires do. Being shocked with electricity is not fun. Don't do it. Been there, done that. I wish I could say it's only happened to me once. And it's happened to me like 4 times. It's great. So I'm still here, luckily, because I wasn't grounded. I was not connecting any other wires. I was lucky enough to not be grounded in any way. But it is pure luck. So most of the times it happened to me because I used to do HVAC work. I used to replace furnaces. You know, that's what I did back before and through college. And working with my dad, I would say, hey, did you, he'd say, go ahead, disconnect the wiring. And I say, so you flipped the breaker, turned it off? Oh yeah, it's off. And there I am disconnecting the wiring, and guess what? Still hot wires. He didn't really flip the breaker. So I did learn the hard way. You need to take responsibility yourself to make sure that you are operating in safe environments. Your dad's not going to look out for you. Turns out that sometimes isn't the case. So, when dealing with electricity, yeah, you need to actually be very safe about it. Okay, I think that about does it. Yeah. Yep. There, go through my summary. That's it. I'm done. So, let me just kind of leave it at that for now. So that's my conceptual recap. I think it's my analogies that I really wanted to get across to you guys. Maybe you guys don't care about it and you think they're totally silly, but I'm not even joking. When I go into grocery stores, I really do think about series versus parallel circuits because I think it's kind of a fun little reminder about how there's a difference where if I want to add a resistor in a parallel circuit, it's going to make less resistance overall because it's yet another pathway. If I add a resistor in series, then that's going to cause more resistance total. So I go to Costco, I check out, they check your receipt at the door, you have to go bring they make you take the cart back. It's more resistance, one thing after another in series. So I hope that helps in some conceptual ways, and so I think we'll leave it at that, and that's hopefully our last little lesson. So that's it. Let's end it.